So here we have a conductor that has this shape. It has two holes of diameter A, and everywhere on this region there is a current I flowing out of the page, everywhere on this region. So the current density of this object is just the current divided by the area where the current is flowing. So the area where the current is flowing is the area of the big circle minus the areas of the two holes. So if we evaluate this expression, we get this, 2I divided by pi a squared. So now that we have the current density, we can see that the total object can be modeled as the superposition of two objects. A solid cable with no holes where current flows out of the page, and two cables where current flow into the page. If we add all those objects together, we get something equivalent to our original object. So now we have to determine the current in these little cables. So the current in these cables that flows into the page is equal to the current density times the area of those cables. So we know the current density, and we know the area of these cables. So the current flowing into the page in these cables is I over 2. Now out here in the big cable, the current that flows out of that is just the current density times the area of the big cable. So we know again the current density, and we know the area of the big cable, just pi a squared. So we know the current flowing in this big cable is 2I. So now we got to calculate the field of these separate objects, and we can do that with Ampere's law. So here's our total object, and at point P1, that's up here a distance r away from that line, the magnetic field at this point that points to the left due to the thick cable is equal to this. The magnetic field pointing to the left is equal to mu naught times the current of the big cable divided by 2 pi r. We know the current of the big cable, and we know the distance to point P is r. So that's the magnetic field pointing to the left. Now the magnetic field pointing to the right is just the contribution from this cable, which is just mu naught times the current of that cable divided by 2 pi the distance to point P, and the current of this other cable produces another magnetic field, which is equal to this. So what is the enclosed current of each of those? Well, is the current through each of those cables, which we know is I over 2. So if we plug that in, we get this as the total field going to the right due to the two small cables. So the total field at point P is, well, we take the total field to the left, so we take the total field to the left minus the field to the right. And we just plug in what we have for the field to the left and the field to the right. So that means that the total field at point P is going to be this. Field to the left minus the field to the right. The field to the right is produced by the two small cables, and the field to the left is produced by the one thick cable. So this expression simplifies to this. If we do a little bit of algebra, we can simplify it to this. Okay, so that's what the total field at point P1 is equal to, and it points to the left. So now we are interested in finding what the total field is at this point over here, P2, at some distance r from the center. So in this case, we have to consider again the field produced by each of the separate objects. So if we take these cables where the current is flowing into the page, the distance from the center of those to P2 is given by this. Here the current flows into the page in these cables. So the magnetic field points in this direction for that cable, and for this cable in that direction. And they form these angles theta with respect to the vertical. So now we can easily calculate the distance, or the cosine of the angle theta, which is equal to that. And so then the total field pointing down is just, the field of one of the cables times the cosine of the angle. And if we take into account the two cables, we just multiply that by 2. So now we have an expression for the total field pointing down at point P2. So we have this term plugging in the value for the enclosed current and for cosine of the angle. So now we know the total field pointing down at point P2. Now what about the field pointing up? Well, this has current flowing out of the page everywhere, so that produces a field pointing up at P2. And the magnitude of that field is just given by this expression where the enclosed current is just the total current of the thick wire, which is that. So the total field pointing up is this. Now the total field at P2 is just the field pointing up minus the field pointing down. So the total field at P2 is pointing upwards, and it's just the field up minus the field down. So we just plug in what we have for these values, field up, and for field down we have this. And then we could just simplify this expression by doing a little bit of algebra, and we could write the whole thing out as this thing right here. So this is a total magnetic field at P2 and it points upwards.